We are really excited to welcome Dr. Mehrdad Shokrabadi to talk to us today about rapid damage assessment after earthquakes using the ATC 20 procedure. And so the way this workshop is going to work is he's going to give us a quick presentation, probably about 30 minutes or so, and just giving us an overview of how to assess buildings after earthquakes have happened. And then we're going to have an activity that will be really hands-on. So we'll give a series of case histories and we'll kind of go over them as a group, take a look at how we would rank those buildings, and we'll use the ATC 20 as a reference. And then we'll have a little poll in the Zoom and bring everything back together for a discussion before we move on to the next case history. And at the end of this session, Dr. Erica Fisher will be talking about how to get involved with Reconnaissance and EERI, even as a student. So it should be really great. So again, we'll go over some more details about the activity as we get after the presentation, but first I'd like to introduce our first speaker. So Dr. Shokrabadi specializes in performance-based earthquake engineering, seismic hazard recognition and mitigation, and nonlinear modeling and analysis of various structural systems. His work has focused on the design and implementation of efficient algorithms to tackle large-scale problems, improving the current seismic risk analysis methodologies and adoption of machine learning techniques for rapid post-disaster damage assessment. While earning his PhD, Dr. Shokrabadi developed a probabilistic framework that allows explicit consideration of aftershocks in seismic risk analysis. The proposed framework integrates heightened seismic hazard following a main shock event with increased vulnerability due to main shock damage. I don't want to take up any more of his time, so I'm going to go ahead and stop sharing my presentation, and we will get going with the main event here.
All right, hello everyone, and thank you, Kelly, for a great introduction. So if you don't mind, I'll turn my video off because I'm not really sure about how good my internet is. So then I would start sharing my screen with you. So everybody can see my screen?
Yes.
All right, perfect. So hello again, everybody, and I hope you've been enjoying your workshop so far. So my name is Mehrdad, and I'll be with you for the next about 75 minutes as we are going over the ATC 20's concepts about earthquake, safety assessment, and a couple of practice exercises on how we can apply the ATC 20's guidelines to real-life structures. So a bit about my background. I'm an engineer with the firm Exponent, and before that, I was a PhD candidate at UCLA in structural engineering. Basically, what our firm does is to do failure analysis. So if there is a building that has suffered some sort of damage due to any kind of event, earthquake, explosions, construction deficiency, hurricanes, or anything else that you can think of, our firm would advise our clients on the implication of the damage to the building's safety and what they can do to address the damages and restore the building to its normal functionality. So to give you a heads up about what the presentation today is going to look like. So basically, the publisher of the manual, ATC itself, offers training for ATC 20 that are about 4 hours, but here we only have 30 minutes. So obviously, our presentation is going to be a little bit more concise. But as you all know, engineering is all about learning the fundamental concepts of a topic and then learning how to build on that and learn the details later. And I'm sure that you are all very bright and enthusiastic engineers that are capable of that. So a bit about ATC 20. So it was first published in 1989 and it was revised in 2005. Basically, it was supposed to be a pocket manual for field inspection of the structures that are affected by an earthquake. So at the same time, it also has a list of the components of a building that are the most vulnerable to an earthquake. So basically, sometimes it can be used to some extension as a guideline for design and retrofit of buildings. So a brief outline of my presentation today. So basically, first I'll go over safety assessment and reconnaissance after an earthquake. So ATC 20 is mainly intended for the first one, safety assessment. So it's important to distinguish between these two. And then I'll go over some of the ATC 20's concepts and then its guidelines for inspection of the different types of structures. And ultimately, some tips for doing a successful field inspection. So before I start going over the ATC20 concepts, it's good to get a better idea of the intentions behind the development of ATC20 and what it can or cannot be used for. So basically, ATC20 is a document developed mainly for the purpose of the safety assessment of various types of structures after an earthquake. So it is important to note that it is not intended for earthquake reconnaissance, although I should say that many of these guidelines is applicable to both. So basically, to distinguish between safety assessment and reconnaissance, the goal of earthquake safety assessment is to, as rapidly as possible, identify unsafe buildings that put the lives of their occupants into danger, and also make sure that the occupants of safe buildings can go back to their buildings. On the other hand, the objectives of reconnaissance are a bit different, so they are broader and more long-term. So basically, the goal of reconnaissance is to document the sizing performance of the buildings in as much detail as possible, both and I mean both components that work and both the components that did not work, the components that met their design objectives and those that failed to do so, and then use the findings to propose revisions to the current design code and practices or come up with future ideas for research. So to explain that a bit more, so basically, when you're doing earthquake safety assessment, all you need to do is to tell the owners of the building whether their building is safe for them to return to it or whether they need to evacuate their property within a short amount of time that you have after an earthquake. Whereas when you're doing earthquake reconnaissance, you have more time in your hand to thoroughly detect what happened to buildings during an earthquake and what lessons can be learned from their performance after an earthquake. As an example, if you encounter a building with cracks on its interior and exterior, if you encounter a building that you see cracks on its exterior and interior, and those cracks are not extensive and are not extended into the structural elements, then if you are doing safety assessment, all you have to do is to tell the owners of the building that they can continue to stay in that building and address the problems later. But if you are doing reconnaissance, then what you have to do is to spend a lot more time on that building, documenting all the details of the cracks, and then trying to figure out why they happen in the first place and what can be done to prevent them from happening again in the future. So basically, the goals of reconnaissance are a bit more broader and more long-term compared to earthquake safety assessment. So if you're doing reconnaissance, your goals should be purely objective. So basically, you're concerned with documenting what went wrong in a building and what seismic details in that building work, as it was the intention of the developers. So these goals could either come from the company or the institution that sends you into a region for reconnaissance, or if you are self-deployed, then you should set your own goals and try to stick to it as much as possible. So there is also, of course, a safety assessment component to each reconnaissance. So you have to make sure that if you're about to enter a building, that building is safe and that you're allowed to enter it. Also, if you're doing some sort of resiliency assessment for a community, again, you have to probably document whether a building remains safe after an earthquake or not. So why ATC20 is not ideal for reconnaissance? So basically, ATC20, basically, as I mentioned before, reconnaissance is a purely objective task where you minimize the involvement of your own judgment in the procedure. Whereas if you're doing earthquake safety assessment, then safety assessment in its nature is subjective. So basically what you do in safety assessment is to observe the conditions of the building, and then you would decide whether that building is safe or not based on your judgment. Also, safety assessment is mostly concerned about what went wrong with the building, whereas in reconnaissance, you would document both. You would document what components of the building work and what components of the building did not actually fail to meet the design objectives. So, and despite all of this, still there are some stuff in ATC20 that's applicable to both reconnaissance and safety assessment. So, chapter 5 to 10 of ATC20 lists in detail and for various types of structural systems the components of buildings that are most vulnerable to an earthquake. So obviously, even if you're doing reconnaissance, you can still use this as a guideline on where to start your inspection and what kind of components in that building you need to look for damage for. And it is also important to note that not all the safety hazards in the building are due to what goes wrong with the structure system of the building. Non-structural components, For example, non-structural components could also pose a great danger to the building's occupants. So imagine a fractured gas pipe, a gypsum wall that is about to collapse, or a hanging architectural component on the exterior of the building that could fall off at any minute. So these kind of non-structural components could also pose as much danger to the lives of the building occupants and those who pass by the building as the structural elements of the building. And so we need to consider them, and ATC 20 actually encourages its users to consider this kind of stuff as well. So now a little bit more about the ATC 20's concept. So first, ATC 20's evaluation process. So ATC 20, so basically the ATC 20 safety evaluation procedure has three main steps: a rapid evaluation, a detailed evaluation, and an engineering evaluation. So many buildings would only see the first two, rapid evaluation and detailed evaluation. And I would say like 95% of the buildings would only see a rapid evaluation, and probably 3 to 4% detailed evaluation, and very few buildings the engineering evaluation. So the first type of evaluation, a rapid evaluation, is actually, as its name suggests, it's a very fast and quick evaluation that you would usually do within hours after an earthquake and would only take between 10 to 30 minutes. So this is an evaluation that can be done by anybody, can be done by building inspectors or disaster workers or a qualified structural engineer. And the goal here is actually to identify buildings that are clearly unsafe and post them with a red tag, or buildings that need further evaluation and post the yellow tag on them. The other buildings that you would observe are posted the green tag, and we will let the occupants to go back to their buildings. So for buildings that are posted with a yellow mark in the rapid evaluation, then a more detailed evaluation can be done by qualified structural engineers. So this is a type of evaluation that usually takes between 1 to 4 hours and is more detailed and involved compared to a rapid evaluation. So the last type of evaluation, an engineering evaluation, is not actually addressed in ATC 20, but this is something that the owners of the buildings that are concerned about the safety of their building can do. They actually would hire their own engineer, and that engineer would evaluate the safety of their building in a time span of days to weeks. So as I mentioned in the last slide, a building can be posted with 3 different types of placards. So basically, the first placard, the green tag, tells the occupants of the building that they can safely return to their building and there are no major safety concerns with their building. The second tag, a yellow tag, would basically tell the owners that there are some concerns with the safety of the entire building or some portions of it. So depending on the situation, either the owner can return to the building but avoid some certain areas of the building that you would mark, or that they only can return to their building for a very short period of time to retrieve their own personal belongings. And ultimately, the unsafe or the red tag means and it's unsafe for the occupants to go back to the building before the damages to the building is addressed. So the first type of evaluation, rapid evaluation, is actually, as I mentioned before, was mostly done in the field, and it is what we are doing today as part of our exercise. So I would go over the details of this type of evaluation a little bit more. So this is a type of evaluation that's done in a very short amount of time, usually between 10 to 30 minutes, and can be done by anybody. Can be done by you as a qualified structural engineer, or can be done by a building inspector or a disaster worker. So I would say this is the type of evaluation that you would do from the window of your car by only looking at the exterior of the building for the most part. So the main goal here is to rapidly identify the buildings that are clearly unsafe, or the buildings that you cannot decide whether they are safe or unsafe, and then pass them for further evaluation down the road. So when you're doing a rapid evaluation, basically you're looking for 6 main key points in a building. And these are the points that are listed in this table. So it's basically, these are the things that if you observe in a building, you would either post it as an unsafe, or that you would ask for further evaluation of that building. So if you see a building that has partially or completely collapsed, or has moved out of its foundation, or if you see a building with a story that's leaning and is out of plan, or if you see a building with obvious damages to the structural component, or massive failures in the ground, then that building is unsafe and needs to be either repaired or demolished. So for other things like for example a collapsed chimney or a non-structural hazard like the possibility of a toxic spill or a broken gas pipe, then it's left up to you to decide whether you want to post that building as an unsafe or just barricade the area that's unsafe and let the owners return to the building and use the remaining parts. So the second type of evaluation is the detailed evaluation. This is something that's done only by qualified engineers that have either more time in their hands. So this is a type of evaluation that would usually take between 1 to 4 hours and is a lot more involved and complicated compared to the rapid evaluation. So now let's take a look at some of the things that we should be on the lookout for when we go for an inspection in the field. So basically, there are a few known planar and vertical configurations that are known to cause problems in earthquakes. So buildings with vertical planar irregularities are usually one of the major sources of concern when an earthquake happens. So if you see a building with any of the types of the planar or vertical irregularities that you're seeing here in this slide, then you should be on high alert and look for potential damage in that building. So as far as the vertical irregularity go on the left side of this slide, if you see a building with a soft story where columns at the first story are seen and distantly spaced to make room for litter or parking spaces, then these kind of buildings have failed times and times again in the past earthquake, and you should take a very close look at the possibility that they are unsafe for the occupants to return to. So building with setbacks have significant changes in their mass and stiffness along their height and this kind of changes in the mass and stiffness could result in concentration of forces at the locations that the change happened. So similarly, if you see a building with a rooftop tank, because the dynamic characteristics of the rooftop tank is completely different from the dynamic characteristic of the building, then this could result in concentration of forces at the structure elements that support the roof tank and damaging them. So if you see a building that's located on a hillside with long placeable columns on one end and short columns on the other end, then these buildings are susceptible to damage at their first story. Buildings with coupling shear wall system, and this is a very common structural system for mid and high-rise building, could also see damage at the components that connect the shear walls at the both sides of the opening. So also buildings with different dynamic characteristics that are located close to each other could push against each other and damage each other. So as far as the planar irregularities go, then anything in the plan of the building that's not a simple geometric shape should be a source of concern because of the potential for concentration of forces. Also if you see a building with a large opening in plan, then you should be on high alert because usually there is a concentration of forces in the elements that link the two portions of the slab adjacent to the opening, and this could cause damage in those elements that connected to the two sides of the slab. So chapters 5 to 9 of ATC 20 list the most common structural system with handy sketches that you see here that mark the areas of the building that could be the most problematic. So basically, each chapter is focused on a specific structural system. You will also see a table in each chapter that lists the most common failure types with each building and what kind of tag you should post on that building if you see this type of failure in the building. So chapter 5 is about wood frame buildings. Basically, wood frame buildings would generally perform well in earthquake. The most common issues in this type of building is the separation of the chimney or problems with the foundation and the creeper wall that connect the building to the foundation if there is a raised floor system in the building. So masonry buildings, especially on reinforced one, they've been a major, they're actually a common construction type in older buildings or less developed areas. And in the past earthquakes, they've been a major source of disaster. So these buildings have very heavy and fragile buoys that could easily collapse even under moderate ground shakings. Also, many of these buildings, the walls and the floors are built separately and then later connected together. So in many earthquakes, they would separate and then the entire building would collapse. Tilt-up construction, so basically are a type of construction that involve lifting or tilting precast concrete panels to form the walls of the building. So basically in this type of buildings, since the floor and wall are built separately, then there is a potential for the separation at the joints between the wall and floor, and you should closely inspect these joints if you are inspecting a precast tilt-up concrete structure. Chapter 8 is about concrete, reinforced concrete structures. So in concrete shear walls, the primary source of concern is the damage between or at the corners of the openings. Also in concrete shear walls, the majority of the forces are developed at the base of the wall. So you should closely inspect the base of the wall for damages to the concrete. And if the reinforcement is exposed, then you should be on the lookout for the damages to the reinforcement. If you are inspecting a concrete frame building, then you should look for damage at the joints between beams and columns, or at the columns, or at the base of the columns at the first story, since the majority of the forces are developed at this location. Chapter 9 is about the steel frame buildings. So steel frame buildings usually perform well during an earthquake, but again, past earthquakes have shown that there are some vulnerabilities with them. So basically, the major source of concern in this type of buildings is the connection between the beams and columns, or beam columns and braces. So also, since these buildings are usually soft and have relatively small stiffness, then it's likely that you would see large and significant residual drifts in them that would make the story look out of plan. So there are some other chapters in ATC 20 as well. So basically, chapter 10 is about mobile homes. So in this type of construction, the most concern is at the connection between the home and the foundation. Chapter 11 is about geotechnical hazard. So things like ground failure, liquefaction, and any type of hazard that's posed to the structure by the failures in the ground. So this is something that needs to be closely examined by a professional geotechnical engineer. And chapter 12 is about non-structural hazards. As I mentioned before, it's not just the structural members that could pose a danger to the lives of the buildings occupants, but it's anything that non-structural. But things that are non-structural could also pose significant danger to the lives of the buildings occupants. Things like a broken gas pipe, a falling hazard, or things like that. And you should be on high alert, for this kind of stuff as well. So there are some appendices to ATC 20 as well, appendices that would actually have guidelines on how you would deal with the people, the homeowners, the authorities, and a chapter on how you would, on the safety tips that you have to follow when you go to the field, a chapter on what kind of permission you need to enter a building, and finally a lot of example and case study with full grayscale photos from buildings that have sustained some sort of damage during past earthquakes. So my last few slides are about the steps that you have to take to be able to do a successful field inspection. So basically, the first step is to prepare as much as possible. So have your own field manual with you, print out the forms that you need, and download all the apps that can help you in data collection. Look at the Google Earth photos, and get an idea of how the region looked like before the earthquake happened. You should also get an idea of how intense the earthquake was by looking at the recordings of PGA and intensities at the station close to the location that you are going for an inspection. Also get an idea of how the buildings in that region look like and what type of a structural system they use. So check news report and social media for any kind of reports on the extent of the damage in the region. And also, if you know anybody in the region, we should reach out to them. We should reach out to them to get as much information as possible. So when you go to the field, before you approach a structure, you should look around to make sure that there are no major safety concerns to you and your life before you enter the building. Also be on the lookout for any kind of non-structural hazard, broken gas pipe, or any kind of falling hazard could seriously injure, could result in serious injury or even death if you are not careful. So when you are entering a building, try to get an idea of the interior layout of the building and also what kind of occupancy it has. Is it like a main infrastructure building that is very needed, very much needed after an earthquake, or is it just a simple residential building? So identify the structure system of the building that you are inspecting. So, and once you do that, find the chapter in the ATC 20 that would allow you to, that would actually tell you what kind of components you should be looking for to see damages. And also check for the irregularities in the plane and vertical and the height of the building that we just discussed. So first, you should identify obvious damages and movements. And if you're in doubt, you should just follow the load path the same way that the load that the earthquake loads would transfer from diaphragm to vertical members and from vertical members to the foundation of the building. You should only enter a building if it's necessary and if you're allowed to and if you think it's safe. And once you're in the region, ask yourself, what's your main objective here? Is it safety assessment or is it reconnaissance? And given the conditions of the building that you're expecting, how likely it is to sustain more damage as aftershocks keep happening? And also, are there any other dangers in the region that actually you should consider when you are assessing the safety of the building? And ultimately, and most importantly, once you go back home, you should post-process the data that you got, sync and sit on them, and also upload and share them with your colleagues. So my last slide is on some of the tools and that you should have with you when you go for a field inspection for your own safety. Hard hat, heavy safety vest, sunscreens, and water are necessary tools that you should always have with yourself. You should have a clear idea of where the nearest medical facility is in case you needed it. And then you should always take a look at anything. You should always take a closer look around yourself before you enter a building. Just make sure that there is nothing that would jeopardize your life. And each earthquake is different. Just because you've been to many inspections before, doesn't mean that everything is going to look the same in the current inspection. Just always be aware of what's around you. And ultimately, it's you that mostly responsible for your own life and the life of